design of sewing machines to the launching of space probes to Jupiter and beyond, Newton's laws form the basis of any model. They allow us to predict and plan complicated motions. So powerful are Newton's laws that it's hard to imagine a world without them. So, what was life like before Newton? Well, what was life like before Newton? How did people explain motion? For example, the motion of this card. Well, at first sight, you might say, the natural state of motion of the cart is to be at rest. Whoa! Well, if I wanted the cart to keep moving, then this horse would have to keep pulling. In fact, it would have to exert a force. Well, in fact, the horse would have to exert quite a large force indeed. So, you might actually believe that the natural state of motion of the cart is at rest. Consequently, whenever you see something moving, you might believe that there has to be a force acting on it to keep it going. Well, that sort of makes sense, doesn't it? Well, it made sense to people for about 2,000 years, from the time of Aristotle to the 17th century. It took the genius of Newton to realize that these common sense ideas are not the best way to model motion. The clue to understanding motion comes from considering much simpler things. Well, a smooth ice rink gets rid of a lot of the friction, and it's level, so there's no effect of gravity either. Well, what's going to happen to motion under these conditions? For example, to the motion of an ice puck. Well, once started, an ice puck will move across the ice with almost constant velocity in a straight line. Well, even an ice puck will slow down and come to a halt. You'd think that for any particle, you'd need to keep applying a force in order to keep it moving. Well, that's what people thought before Newton. They thought, where there's motion, there must be a force. But Newton said, no, that's not the case. A free particle, that is, a particle without any forces acting on it, must either remain at rest or move with constant velocity in a straight line. And that's just a statement of Newton's first law. It means that you don't need any special explanation to explain uniform motion. That's what happens in the absence of external forces. But what about this sort of motion?
Each time it's struck, the puck's motion changes, and Newton would say that indicates that a force has been applied. In between hits, the puck is behaving almost like a free particle.
Newton's second law tells us there's a link between the deviation from uniform motion and the applied force. The question is, what form does that link take? Newton gave a very definite answer to that question. The form is F equals ma. Force is equal to m times acceleration. Now, m is a constant, which we'll have a lot to say about later on in the program. But for the moment, the important thing for us to notice is that force is proportional to acceleration. Acceleration, the deviation from uniform motion. Well, what does that mean experimentally?
To have a closer look at Newton's laws, we've set up this piece of apparatus, which does the same sort of job as the ice rink, but even better. To cut down friction, this glider rests on a cushion of air. The air coming through tiny holes along the track. Just like in the ice rink, this is level, so gravity is not going to affect the motion. And of course, by using a track, we're confining ourselves to one dimension. These after images are left on your screen by a piece of electronic processing. What we've really done is to freeze the position of the pointer on the glider every 3/4 of a second. So you see where the pointer was at 3/4 of a second, 1.5 seconds, and so on. Now, the equal spacing of the images means a constant velocity, or zero acceleration. And that's just Newton's first law. With no force, the glider was just a free particle. But Newton tells us much more than that. Newton tells us what happens when we do apply a force. F equals ma. Force is proportional to acceleration. So if I apply a force by attaching this string to this glider, we should see an acceleration. Well, now the after images are getting further apart where the glider's speeding up. And from those after images, we can find out something about the acceleration. We start by looking at the graph of distance against time. The timing started when the motion started. After the first time interval of 3/4 of a second, the glider had travelled 0.05 meters. After the second interval, 0.22 meters. And so on. So over the whole period, the distance time plot looks like this. We can get a velocity time plot from this. To get the velocity at any instant, we need to differentiate. We can do this by drawing tangents. At the start of the motion, the tangent has zero slope, zero velocity. The glider started from rest. After the first time interval, the tangent to the graph has slope 0.15 meters per second. After the second time interval, the slope is 0.3 meters per second. And so on. The velocity time graph that we get from that is a straight line graph. The velocity changes at a steady rate of 0.2 meters per second, a constant acceleration. What would Newton have made of that? Well, Newton would have said straight away that the constant acceleration must have been produced by a constant force. You see, F equals ma, so if A is constant, then F has to be constant as well. And that's something we can check directly, because the more force I apply to this spring, the more it stretches. So if a constant force is really being applied, the string should have a fixed extension. There it is, a constant extension, a constant force. Just what Newton would expect. Now let's try a different force on an identical glider. We'll adjust things at this end so that the force is twice as large as it was before. And to check that it really is twice as large, I've got two springs here, two springs just as I had before, side by side, and they've got the same extension as they had before. So the two springs indicate double the force. Well, obviously the glider accelerates more rapidly under these conditions. I don't want to go through the acceleration analysis here, so I've left it as a problem for you to do after the program. But you should find an acceleration of 0.4 meters per second. That's twice the acceleration we had before. So with double the force, we have double the acceleration.
Well, I promised that we'd say a little bit more about this constant m. Suppose I were to do John's experiment with two identical gliders stuck together instead of this single glider. Well, I don't think it needs much imagination to realize that it's going to be harder to accelerate this one. for the same force, this one is going to go to a smaller acceleration. So in this equation, that means for the same force, as this acceleration is going to be less, then this value of m has got to be greater for the bigger glider.
An acceleration of 0.1 meters per second. That's just half the acceleration we had with a single glider pulled by the same force.
Again, we can see what that means in terms of this equation. For a single glider, the acceleration was twice as much for the same force as it was for the double glider. That means that the double glider, this m, was twice as big as it was for a single glider. And for 3 gliders, it's 3 times as much. For 4 gliders, it's 4 times as much, and so on. So you see that this number m, which depends on the object, tells us 2 things. First of all, it measures the reluctance of the object to be accelerated. And secondly, it measures for us the number of gliders. And really, that explains the name that we give to this number. It's called inertial mass, or sometimes mass for short. Inertial because it tells us how we measure it. It measures its inertia to being accelerated. And mass, well, it really measures the amount of matter in the object. So that explains Newton's second law, F equals ma, force equals mass times acceleration. Well, now we have this equation, let's see what we can actually do with it. Well, so far all we can do really is measure acceleration. Now, if I'm going to quantify forces and masses, I really ought to adopt some conventions. For example, the convention for the mass unit is arbitrary. I could choose the International Standard Kilogram, but as you can see from this picture, I'm not going to be able to get my hands on that very easily. So I think it's far better from our point of view to pick as one glider, one standard glider, as our mass unit. Then I can measure force in terms of that. For example, remember in John's experiment, he found that when he had one glider, so that's one mass unit, he got an acceleration with the force he applied of 0.2 meters per second. And that means that when I multiply these two together, it's a very easy calculation, the force turns out to be 0.2 force units. So in fact, one force unit would be really about 5 times the sort of force that was applied in that experiment. Well, we can measure forces that way, but can we use it to measure masses? For example, what about this mystery mass?
We can find the unknown mass by an acceleration experiment. As usual, we'll use a force of 0.2 force units.
Let's find our mystery mass x using Newton's fundamental equation F equals ma. The force John was using was 0.2 force units, and he measured the acceleration as 0.13 meters per second. Putting all those into F equals ma gives this equation. Now, when I solve that equation by dividing by 0.13, I get x to be a little over 1.5 mass units, about 1.5 times our standard glider. In principle, we can use this idea to measure any mass. Now, it may not be quite the way you think mass is measured, but this is really the fundamental way of measuring mass, as a measure of inertia.
So far, all the forces we've used have been applied to the gliders through springs. But Newtonian mechanics is about far more than springs. Look at this. I'll put a wedge under the air track so that it's tilted. Now, there's certainly an acceleration here. Where there's an acceleration, there must be a force.
Well, of course there's a force down the inclined air track. That comes about as an effect of gravity. But what's more interesting is that we can actually calculate the magnitude of that force.
And we can do it on the basis of Newton's second law. F equals ma. Well, a, the acceleration, John's experiment has actually found that, and he got that to be 0.06 meters per second. And the mass, well, we've actually found that too. That mass is 1.54 mass units. So Newton's law tells me that if I multiply these together, I'll get the force in our force units, and that turns out to be 0.09. Well, okay, I suppose that's fairly satisfactory. But a theory is only exciting if you can make predictions. And, in fact, we can make predictions on the basis of this second law. But that will involve John doing a new experiment. And this is the experiment I'd like him to do. Let's consider that inclined air track, and suppose we have our glider on it, and he applies one of his standard forces upwards, and I know that we have this force that we've just calculated downwards. Well, what's going to happen? Here I have a standard force upwards, which is 0.2 force units, and the force downwards, I've just got that to be 0.09 force units. So there's a residual force upwards because, well, 0.09's worth of this will just cancel from the 0.2 upwards, and what will be left will be 0.2 minus 0.09, which is just 0.11 force units upwards. So what do I predict? I predict that the mass will accelerate upwards with an acceleration corresponding to a force upwards of 0.11 force units. Well, let's see John do that experiment.
(0.07 meters per second, this time up the track. So far, we've been looking at gliders on air tracks. But what happens when things fall? In particular, when we drop this from the Clifton suspension bridge, how long would it take to hit the water?
Well, the reason bodies fall is the gravitational force of attraction due to the Earth. To investigate this force, here I've got a standard mass and a standard spring. And if I suspend the mass from the spring extends. The gravitational force on the mass is exactly cancelled by the force in the spring. Now, if I take two masses, put them together, and suspend them from two springs, the extension is exactly the same. The upward force due to the springs is twice as big, and so the gravitational force on two masses is twice as large as that on one. And if we did the same with three masses, we'd get 3 times the gravitational force, and so on. In other words, the gravitational force must be proportional to the inertial mass. So the gravitational force on a body of mass m is mg downwards. In SI units, the constant of proportionality, g, is roughly 9.81 meters per second squared. What does that mean for the time of free fall for objects falling from Clifton suspension bridge? Well, first, we need to define our model for a falling object. The force on the object is mg. Substituting this force in Newton's law of motion gives this equation. So A, the acceleration of the particle, is g. Now, the acceleration is just dv by dt. And integrating the differential equation gives this, where c1 is a constant of integration. Now, in our case, the initial velocity will be 0 at t equals 0. So c1 is also 0. To work out how position changes with time, we put v equals dx by dt, which integrating gives x. Again, c2 is a constant of integration. Using the initial condition x equals 0 at t equals 0 gives c2 as 0. That's x in terms of t. But what is the value of t for a given value of x? Rearranging the equation gives T equals the square root of 2x over g.
Let's apply this model to the bridge. The height is 77 meters, and g is 9.81, which, substituting, means t is this, roughly 4 seconds. Let's check that prediction. .1 seconds, which compares pretty well with our prediction.
The fact that the gravitational force of attraction is proportional to mass has two important consequences for free fall. Firstly, the acceleration is always uniform, and secondly, it's independent of the mass. It's always g. The model worked pretty well for our experiment at Clifton Suspension Bridge. But is it always a good one? If it is, then these two objects should take the same time to fall. And they don't. So what's gone wrong? Well, the different times are a result of a second force acting on the bodies. That's air resistance. How does the inclusion of this force modify our model? In the first model, we had just one force acting on the body, mg downwards. Now we have a second force, r, which resists the motion, so it's upwards. For simplicity, we'll assume the air resistance is linearly proportional to the velocity. So the net force is mg minus kv downwards. Newton's law of motion tells us that the acceleration is equal to g minus kv over m. So if we write a as dv by dt, we get a differential equation, which is separable and can be solved to give v. C1 is the constant of integration. And as the initial velocity is 0, C1 is equal to minus mg over k. Now when t is very large, the exponential term is very small. So the velocity tends to vt, which is equal to mg over k. So when there's air resistance, the velocity tends to a constant value, rather than increasing without limit. To check this model in the studio, we need a more viscous fluid than air. So I'm going to drop a ball like this into a tank of glycerine. We know the mass of the ball, its diameter, and the viscosity of glycerine. And using these values, the model predicts the velocity should vary with time like this curve. In particular, the terminal velocity is 0.12 meters per second. So, now for the experiment. As we expect, the velocity tends to a constant limiting value. Let's look at the motion in more detail. Using afterimages, we can plot this distance time graph and get the velocities by drawing the tangents. The velocity time graph looks like this. It certainly has the right shape, and the terminal velocity compares well with the predicted value.
Well, we came here in the first place in search of a free particle, and we found that a nice puck was a fairly good approximation. But Newton's laws don't only apply to free particles. Even when there's friction or air resistance, then Newton's laws still apply, providing we include all the forces.